Yeah, so as I started Tuesday, I will continue on this Demazure character formula and say everything a bit more slowly and a bit more carefully, because I think I was in a rushy mood, so maybe I thought I said things which are not well understandable. So what's that about? So I just repeat our basic setup. So recall we have G a semi-simple Lie algebra, an H a Cartan subalgebra, and if V is a G module, then we associate the character of V, which is just the generating function, or well, let's put lambda in P, weight lattice, of the dimensions of the weight spaces. So, and one wants to calculate these dimensions, or equivalently this function, this character, and we already saw Weil's character formula and this trick to express these dimensions by means of a vector partition function, and now this gives another possibility to do this. So what's P again? P, that's the what we called weight lattice. Or now that I introduced this notion of integral weights, so this is the same thing as the set of integral weights. And this is by definition the set of weights, so the set of linear forms on the Cartan, such that there is a module such that V lambda is non-zero. And we saw that this is actually a lattice. Did we see? Well, I told you, and I gave some indication on the proof. So P is a lattice. And what's the rank of P? That's just, well, the dimension of H. So, yeah, let's look again at some low-dimensional examples. Say, for rank 1, we know our favorite example, the group, is SL2. So the rank is 1. So P is just Z times, well, let me write down more. So P is isomorphic to Z because it's a rank 1 lattice. And which isomorphism did we choose? Well, we just picked one generator omega and sent this to 1. So usually as we wrote it, K goes to K omega, right? This was our isomorphism between Z and P. What else do I need to say? And so if I have a representation V, then the character V, there were these two interpretations, to see it as a function or as a formal object. For this discussion, let's take this point of view of a formal object. So this is an element in the group algebra CP. So this is the formal viewpoint. character as an element in CP, which is the vector space with bases symbols e to the lambda in P. So this is the general definition, and in our case this is just the vector space. Well, so these are, I can write these as e to the k omega, or k is any integer. Yeah. So if I have a character, that means I have a linear combination of these. So I have a linear combination of these. So I just think of this as an infinite row vector. For example, what's the character of V3? The highest weight is e to the 3 omega, and the corresponding weight space is one-dimensional, so the coefficient is 1. Plus, then there is e to the omega, e to the minus omega, e to the minus 3 omega. And I write this sign for it. It's not really equal, but according to this obvious isomorphism that I just identify linear combinations of these e to the k omega terms with row vectors where the components are indexed by z and the index is just the k. Then this is the following row vector. There are an infinite number of 0 to the left. Then there is a 1, so this is, this one here. So this is at the minus 3, minus third coordinate, or minus third coefficient. And there is a 0 at the minus second coefficient. Then there is a 1 at the minus first coefficient, and so on. 1, 0, 1, 1, 0, 1, 2, 3. And then there is an infinite number of zeros again, right? So does it make sense? And now I just, I use these interpretations interchangeably. Usually people write down characters this way as a linear combination of these e to the something monomials, but if I think about it in terms of linear algebra, I prefer this image just as it being an infinite row vector, an element of c to the z. So let's have a look at another example for rank 2, just to make sure that we understand this correspondence between these characters and these linear algebra infinite objects. So another example for rank 2. So here we should take G equals SL3. This is the example we studied most so far. And the let me recall the basis for the dual of the Carton there. So the root system looked like this. This was this hexagon, right? So there's 0. Then there is let's call the simple roots alpha 1, alpha 2. Then there's alpha 1 plus alpha 2, minus alpha 1, minus alpha 1, minus alpha 2, and minus alpha 2. So these were the roots, and then we also know these level hyperplanes. All right. Yeah. Oh, which is not too good. So these should be equidistant. So this gives the pairing with alpha 1 check is 0, 1, 2, minus 1, minus 2. And then there is this other set of level hyperplanes, which is important. So this is alpha 2 check equals 0, 1, 2, minus 1, minus 2. Do you understand how I produced this picture? Does it make sense? Good. So, and then there's this theorem, maybe I didn't, I'm not sure whether I explained this. So exactly, so the P, what's P? Set of integral weights, or let me state it as a lemma. Or, yeah. I think I at least said it, but maybe I didn't write it down. So for lambda in H star, lambda is in P. So lambda actually does occur in as a weight in a module if and only if lambda alpha 1 check is an integer and lambda alpha 2 check is also an integer. Right. So this is also this generalizes to other examples also. Now I wrote it down for SL3. So this explains why these weights are also called integral weights, because these pairing numbers are integers then. So here, wherever we have an intersection of these red and green lines, there is an element of the weight lattice P. So what's a character? So well, first let's write down the character of the adjoint representation. So I write character of SL3. So seen SL3 as an SL3 module by the adjoint representation. And then, yeah, right, we know these are the roots. So these are weight spaces, and they all have dimension 1. So this is e to the alpha 1 plus alpha 2 plus e to the alpha 1 plus e to the alpha 2 plus e to the minus alpha 1 minus alpha 2 plus e to the minus alpha 1 plus e to the minus alpha 2. And then there is 0 is also weight, and the corresponding weight space is two-dimensional, because these are the diagonal matrices, right? And it's 3 by 3 matrices, so diagonal matrices should be three-dimensional, but then there's the restriction that the trace is 0. So this is two-dimensional, so there is a plus 2 e to the 0. So this is the character of the adjoint representation. And again, I think of this as well, it's kind of an infinite matrix, but the easiest thing to think about this is to think about it in terms of the picture. So the coefficient of e to the alpha 1 plus alpha 2 is 1. So the easiest thing to visualize this is that there is a 1 attached to this dot here representing alpha 1 plus alpha 2. So let's say, let's draw the root system again to have a point of reference. So this is 0, alpha 1, alpha 2. So what giving this information is equivalent to annotating this as follows, right? I have a bunch of 1s there and a 2 here. So in fact, the information of giving a character, so giving a polynomial or giving a linear combination of terms of the form e to the element of p, just amounts to associating a number with every element of p, and I'm using the implicit convention that wherever I don't write a number, this is 0. So if I wanted to be more precise, I would have to write all the infinitely many zeros there and write lots of dots because there are always more zeros. Right, so this is but this is what happens. So if we really to write things down, it's best to omit the zeros, and then we just attach some numbers to points in the plane, and these represent the dimensions of the corresponding weight spaces, and this is equivalent to writing down the character. Right? Good. So what's the idea of this Demazure character formula? So we define linear operators. D as alpha, where alpha is an element of the base. So it's a family of finitely many linear operators, and each on CP. So any of these operators gets a formal linear combination of these e to the lambda terms and produces another formal linear combination of these e to the lambda terms. Or I prefer to think of it in terms of these infinite vectors. So then this just means for the rank 1 case, this is an so explicitly for SL2, then there is just one simple root. So there is just one Demazure operator, and this acts on infinite vectors and produces, it takes an infinite vector and produces another infinite vector, or generally there are several of those D as alpha, and they act on vectors indexed by the weight letters, right? So an element of C to the P is, I don't know, it's partially, everything I'm saying is just playing with words, right? So if I write this CP, I think of the character as a formal linear combination, and if I write C to the P, I think of this as a vector indexed by the weight letters, so this is something like an infinite collection of numbers as written down here. Does that make sense? So the idea is to define such a set of linear operators and obtain the character of any irreducible module. And we learned that the irreducible modules are parametrized by these dominant integral weights. And the idea is to get this by iterative application of these operators D as alpha. So let me define these operators again. So I define a Demazure operator for each simple root. So I say let alpha be a simple root, so an element of a base. So I have to define D as alpha, the corresponding Demazure operator. So, and as it's a linear operator, it's enough to define how it acts on a basis of CP. And so basis elements are of the form e to the lambda for lambda in P. So what's that supposed to be? Well, I think I wrote down this formula before. Sum from A from 0 to lambda alpha check lambda minus I, not lambda, e to the lambda minus I alpha, right? So this only makes sense if lambda alpha check is larger or equal than 0, otherwise there are no summons here in the sum. So now the other cases, they are just well, if you think about how to make sense of this sum when this is smaller than 0, this is what you'll come up with. So let me write it down explicitly. Right. So if there is the upper bound is 0, this is the last case we captured here, then there is just one summoned in the sum. So if the upper bound is -1, there should be no summons in the sum at all, and then of course the sum should be 0. What happens if the upper bound is even smaller? Then, well, for -2 there should be -1 summoned. What should this mean? Well, there should be one summoned then, but with a negative sign, and Oh, anyway, let me just write it down. So here I is from lambda alpha check plus 1 to -1, the same thing. So it looks kind of weird, this definition, but if you think about it, this is just the canonical way to define this sum when the upper bound is negative.
Why do we want that 0 right there? Why not just say from -1 and lower? We'll use our bottom case.
Well, if we do this, then there would be a sum from 0 to -1, right? If we
right, so you have to tweak that bottom one a little bit, but I guess.
Yeah, maybe it's, I don't know. So the way I see it is, it should, if people thought about sums correctly, then this definition, this line in the definition should be sufficient. But as I said last time, for Riemann integrals, people think about this about this a lot. What is integral from 2 to 1, f of x dx? Well, that's just integral from minus integral from 1 to 2, f of x dx. So, but when it comes to sums, people just don't think about phenomena like this. So some people would say if the upper index is lower than the lower index, then automatically there are no summands, so the entire sum will be 0, which is also a possibility to define it, but which is less nice than, well, this one corresponds to this one. So, and I think why people, so if you look into a paper, then these three cases will usually be written out explicitly, and this is just to eliminate any ambiguity, right? So now, if I'm in this case, then the sum is from -2 plus 1, so from -1 to -1, so it's a good sum. Here it's just written 0, and so if I distinguish the three cases, then I always have sums with at least one summand, so it's clear.
I guess the question comes in as to why not just on the bottom one start our index at lambda alpha check and not lambda alpha check plus 1, and then erase our 0. Why is there a reason behind this convention, or because essentially we're doing this, not quite doing the same thing, but
well, no, that wouldn't work. So, right, if we can do the index shift, of course, here go from eliminate the +1, right? And we would have to write -2 here, I guess. And here we would have to add a +1 here. I don't know. It's not so. Let me not discuss it anymore. So this is one way to define it, and just think about it. Maybe you find a better way. So for me, personally, the way I like best is just to define, to explicitly say what do I mean by a sum when just to introduce a rule like this, and then you can, after you introduce this, you can omit everything else. But so with this definition, it's correct, and everybody can understand it. So this is the standard way to write it down. Yeah, let me tell one funny story. So you know this Gauss formula, I from 1, say from 0. Now we have to be careful. I from 0 to k, I. That's k plus 1 divided by 2, right? So, but for which k? So that's exercise. this is supposed to hold for all integers k. Find the correct definition of the sum sign. Right. So, of course, this is a well-known thing when k is non-negative. But if you just define the sum in the spirit of this, then it will extend to all integers. Anyway. Yeah, let me do some examples for these Demazure operators. And let's start with SL2. So that's a rank 1 example. Let me write it down first as characters, so as formal linear combinations of e to the something, and then as these infinite row vectors. So, well, as usual, our simple root is the alpha, is called alpha, which is 2 omega, and yeah, that's it. So there is only one Demazure operator, the one associated with this root alpha. And what happens if I apply it to some monomial e to the k omega? Let's just to be sure, let's again consider these three cases separately. K is positive or non-negative, then this is e to the k omega plus e to the k minus 2 omega plus, right, so we're in the first case here. Because there is this lemma k omega alpha check is just k. So if you want this is the root system, so there's 0, alpha, minus alpha, and what are these level hyperplanes here? Right. So these are the level hyperplanes, and then there is alpha equals 2 omega, so there is omega on the level 1 hyperplane, alpha on the 2, and so on. That's 3 omega minus omega. So we have this. So, and how many summons do we have? Well, in the end, it's e to the k minus 2k alpha, omega, right? Because the sums up to k, so we have to subtract k times alpha. Alpha is 2 omega, so we have to subtract 2k times omega. So this is just e to the minus k omega. Then if k equals minus 1, it's 0, this is clear. And if k is even smaller, then it's e to the so let's consider this sum backwards, because it's easier to think about it like this. So the last summand is -1. So here's a minus also. This gives a plus. So we have plus alpha. So that's e to the k plus 2 omega. And there is this minus sign, right, in the beginning. Minus e to the k plus 2 omega minus e to the... Then I add another, right? So if I take the last but 2 summand of this sum, then there is the I is minus 2. So I have a plus 2 alpha here. So that's a plus 4 omega here. And what's the last summand? Or the first summand in this, the way I wrote it down here. That's lambda alpha check plus 1. So it's k plus 1. So it's minus e to the k. I'm getting confused because k is negative now. So the last thing is k plus 1. So it's lambda minus, sorry? Yeah. And that entire thing minus twice because alpha is 2 omega. So that's the exponent. Sorry? No. No. It's should be like this. We really take lambda alpha check plus 1. So it's supposed to be k plus 1. So k is negative. And k plus 1 is still negative, but less negative, I think. Well, let me just try with this because I know the result in the end, and then so this would be k minus 2k minus 1. So this is minus k minus 1. Yeah, that's right. So the last thing is minus k minus 1. So again, what's the thing here? We have to substitute k for the bracket expression. So the last summand, or well, the first summand is as I equals k plus 1. It's lambda minus k plus 1 alpha. So
weird here. You start off with k plus 2, and then you go up to k plus 4, and then somewhere in there we go down to the negative k minus 1.
No, think just of, for example, if k is minus 3.
Okay, that makes a lot of sense. Okay.
Then it's e to the minus 3 plus 2, so minus 1 omega minus e to the, again, plus 2 omega, so it's e to the plus 1 omega, and that's it, right? Because then I'm already minus k, that's 3, and here that's supposed to be 2. So, yeah. Right here. Here I made a mistake. 2 times 1 is minus 2. So here we are good. So it's case minus 3, then it's minus e to the minus 1 omega, because this is k plus 2. Then k plus 4, it's 1. And in the end, it's minus k minus 2. So this is 3 minus 2, so this is 1. So that's it. Okay. So it's a bit mind twisting to work with this. But maybe it becomes clearer when we think about this as these infinite row vectors. Right, so this is an infinite row vector. Say here is the 0 coordinate. Here is the 1, 2, 3, minus 1, minus 2, minus 3. So let's maybe we go through any example. So what happens with this row vector? To which one is this sent by ds alpha? Well, this corresponds here to e to the 2 omega. So lambda alpha checker is 2, so it's certainly positive. And so we're in this case, and this produces ones to the left. And, well, how many ones does it produce? Exactly its coordinate. And that's 2, right? And it produces them with a spread of 2. Right? So this is, if you think of it in this geometric way, it becomes much more easy, right? So if you have a 1 here somewhere in the vector, it produces more ones. How many? As much as its coordinate is, and it produces them with a spread of 1. So if you have a, say there's 0, 1, 2, 3, 4. We have a 1 here at 4. How does the Demazure operator act? Now we produce 4 ones, so that will be 1, 2, 3, 4. So the last 0, minus 1, minus 2, minus 3, minus 4. So the last one has coordinate minus 4. Yeah. Okay, so this is a good way to think about these. You have a 1 in a certain coordinate, say 2, then it produces 2 ones to the left. If you have a 1 in coordinate 4, then it produces 4 ones to the left, and so on. So what happens if, which one can I erase? Where it is. So what about these other cases? Now I explained the cases we were in the first statement here. So again, say this is the 0 coordinate. What happens if we have a 1 in the 0 coordinate? Well, then it produces nothing. It just remains there. What happens if we, it's again the 0 coordinate, what happens if we have a 1 in the minus first coordinate? Then it should produce minus 1 successes to the left, so which means it just cancels itself, and we get the whole vector 0. So what happens if we have a, again this is the 0 coordinate, what happens if we have a 1 here at the -2 position? Then it should produce -2 successors. Anyway, the first one kills itself, and the second one produces a -1 to the right then. So this is somehow how this game works. And one more. Say, here's the 0 coordinate, -2, this is then the -3 coordinate. Suppose we have a 1 here, so this produces again -1s to the right, namely 2. So this is what we get from here by applying the Demazure operator. Makes sense? Yeah. So what's the... If you want, you can try to express the meaning of this operator in your own words, so I can check. Or anyway, so this is the definition, and these are some examples, and how to think of them in terms of row vectors, and then everything becomes a bit more intuitive. Namely, if we have a 1 at the positive coordinate, it just produces children to the left, and if we have a 1 at the negative coordinate, it produces negative children to the right, and essentially that's what these Demazure operators do. And now we have this observation. What's the character of Vk? Well, that's just d s alpha e to the k omega, right? So whenever k is non-negative, then we have this simple representation Vk. We know the character. Yeah, for example, here we did the computation. We know this is the character of V2, right? So there's a e to the 2 omega, e to the 0 omega, e to the -2 omega. And we obtained this naturally just by starting with the e to the 2 omega and then applying this operator. So, so at this point, this is not too, the example is just too small to exhibit its magic. For example, it's not clear at all why we needed this part of the definition just to define it for positive lambda alpha check would have been sufficient. But, well, already we get this kind of character formula, which is a bit stupid, admittedly, in this case, but this is the type of character formula we want to get in the general case also, right? So we start with some monomial, then we apply, well, here it's just one operator. In the other examples, we will need to apply a sequence of Demazure operators, and then in the end we obtain this character. So let me show just how to calculate the character of S. Maybe let me state Demazure's theorem first. Forgot the, I think it's So, well, of course, G is a semi-simple Lie algebra. H carton. And then we need a base in the root system. Fix that. Yeah. Then there is a sequence. Alpha 1, alpha L. So a sequence or just an L tuple. So in delta to the L. So we pick L elements of the base, not necessarily distinct, such that the following holds. For all lambda dominant integral weights, for all these dominant integral weights, by the classification of the irreducible representations, we have this irreducible G module V lambda, and we want to compute its character. So this will be some formal linear combinations of elements of the form e to the mu, where mu is an element of P. And how do we get this? Well, we start with the element e to the lambda. So this is this dominant integral weight. Then we apply d s alpha L. So the Demazure operator associated with the last element of the tuple, d s alpha L minus 1, and so on up to d s alpha 1. Right. So this is what this theorem says. And yeah, for so I just wrote there exists such a sequence, so because I don't want to go into the way it is defined. So, but in fact, there is a explicit description of such sequences. So. Yeah. Alpha 1, alpha L. So I don't want to explain it now, but this theorem is very explicit, even though here I stated it with this a bit vague existence statement. So this is another way to compute characters. Just construct them with this iterative process. You figure out this sequence, which is not too difficult once you know the explicit description. Then then I gave the definitions for the corresponding Demazure operators. Then you just start with a one monomial term e to the lambda, or if you prefer thinking of this in terms of these infinite vectors, then you just start with a vector which contains all zeros, but a single one at the lambda position. And then you just apply these finitely many recursion steps, and you'll get your character. That's how this works. So let me show how to compute the character of the adjoint representation of SL3 by this character formula. So group is SL3. The module is also SL3 itself, acting on itself via the adjoint representation. So the highest weight of this is alpha 1 plus alpha 2. So this can be written as V alpha 1 plus V alpha 2. So I draw the root system together with 0 for reference. First I have to tell you what the sequence is in this case. Here, so there are in general several ones here. An admissible sequence is alpha 1, alpha 2, alpha 1. Right? There are these. This is alpha 1, this is alpha 2, this is alpha 1 plus alpha 2, so this will be our highest weight. And yeah, I happen to know that this is a good sequence. So let's just do the computation. So you see how to handle this stuff. So I start with a monomial e to the lambda. So I start with a monomial e to the alpha 1, alpha 2. So that means in the first iteration step, I just have a 1 here and zeros everywhere else. So now I have to apply, so this is beginning. Now I have to apply D, what's the rightmost element? Alpha 1, ds alpha 1. So maybe I should draw these level sets also. Zero, 1, 2. So my 1 here is on the 1 level plane, so it produces 1 successor to the left. So these two ones are my so maybe I simultaneously write down the formulas. So here I get e to the alpha 1 plus alpha 2, and if I apply the ds alpha 1, I get e alpha 1 plus alpha 2 plus e to the alpha 2. Right? So now I need to apply ds alpha 2. So I need to write down the hyperplanes, level hyperplanes 0, 1, 2. So this one is on level 2, so it produces 2 successors in minus alpha 2 direction. So I get a 1 here and a 1 here. This one is on the 1 hyperplane, so it just produces 1 successor in the minus alpha 2 direction. So what we get at this stage is e to the alpha 1 plus alpha 2 plus e to the alpha 2 plus e to the 0 plus e to the alpha 1 plus e to the minus alpha 2. maybe I continue the drawing with a new. Right, now I have to apply ds alpha 1 again. So let me just write. So this was the current character I was working with. So now I have to apply, yeah, as you say, ds alpha 1 again. Let's write this in red maybe again. So I have to look at these level sets. Yeah. +1. It's hard to draw this. Right. So what happens here? This one is a -1, so it gets cancelled. Right? So this is this second part of the definition where we have 0. This has a +1, so it produces another one. So in the end, we will have 1 here again, but it's 1. Yeah. So this one has a 0, so it just stays there and doesn't produce any offsprings. This one has 2, so it produces 2 ones, another one here, and third one here. And this has a 1, so it produces an extra one here. So, well, magically, everything worked out, and we have this 1, 1, 1, 2, 1, 1, 1. So, yeah, it worked. So maybe this is not too impressive now because this is a small example and I could just tweak things to work. But in fact, yeah, you have to trust me here that this is actually a theorem, and then there is this explicit way to describe these admissible sequences, and it will all work. Yeah, so this is Demazure's theorem. So let me just close by some remarks. The first thing I already said, one can explicitly describe the sequences. Then the second remark is that this, let me write this down. So why is this formula also important? The theory we studied, or the weight theory, I just write it like this. So basically everything we did during the last couple of weeks generalizes to certain infinite dimensional Lie algebras, the so-called Kac-Moody algebras. So what are these? They are infinite dimensional Lie algebras which have a Cartan matrix. Right, so this Cartan matrix associated with the root system or with the base of the root system was somehow crucial in the classification of semi-simple, finite dimensional Lie algebras, and it turns out that for some infinite dimensional Lie algebras one can also produce a Cartan matrix, and we'll get a theory which is very similar. And then yeah, then many of the theorems generalize. But for those, V lambda, so there are also these irreducible highest weight modules V lambda, just as we had them here, but these will be infinite dimensional also. So how does this correspond to this formula? Well, if you write down the analog of Demazure's theorem for these Kac-Moody algebras, you'll see that this sequence of simple roots of elements of delta you need is an infinite sequence. So you would have to apply a Demazure operator, another Demazure operator, still another, and just the process never ends. So you can never really calculate the character of this infinite dimensional representation this way. But one can define subvector spaces finite dimensional ones. Yeah? V W lambda, so they are indexed by an element of the while group. And how does this construction work? Well, I won't explain the construction now, also because time's up. But the idea is just, if you calculate the characters, just stop after a while. You would have to calculate the characters of the irreducible modules. You would also have to start with E lambda, then apply some ds alpha 1, then apply some ds alpha 2, and so on. And you'll never stop. Well, why not just stop after ds alpha k? Then you get some character, and so you get a filtration of the infinite dimensional irreducible modules by these Demazure modules. So these are called Demazure modules. And
yeah. So you get a sequence
of yes.
Finite dimension.
Right. So yeah, maybe I can. Let's see whether there are already many people for the next lecture. No. So I can say something about the sequence. The admissible sequence. So which Demazure operators do I need to? Okay, but this will take. Maybe I don't. You have to go anyway. So, so the thing is, there are the short answer is just there are several admissible sequences here, which I'm not. I would have to say more to make it precise, but. So there's this longest element of the while group, and you fix a reduced decomposition of the longest element of the while group. And this gives rise to such a sequence. And for any such reduced decomposition, you get a different sequence, and you can truncate each of the sequences to the left. So that's why I said you get a, you get a filtration, so you get some finite dimensional subspaces of this infinite dimensional space, but it's not just a linear sequence, but in fact the sequence is a linear sequence that would be parametrized by natural numbers, but it's in fact parametrized by the while group. So it's
each one gives rise to an indivisible sequence, and then each divisible sequence gives rise to this.
Exactly. Yeah. And they are a bit right. So this is it. Yeah. Anyway, so somehow a bit sad that you can't come tomorrow, because I explained this speaker slide. Tomorrow I will explain some formula I proved for these Demazure modules for the some statistical formula about these weight multiplicities. But
for the infinite dimension for X.
well, this is the Lie algebra we consider is one of these Kac-Moody algebras. So it's not one of the Lie algebras we studied here in class, but so-called SL2 hat, so it's connected with SL2, but it's very different. So this is an infinite dimensional Lie algebra, and then, yeah, so this is exactly the situation where the irreducible representations are infinite dimensional, but one can exhaust them by a sequence of these Demazure modules, of these finite dimensional modules. And then, yeah, what we do is just to consider increasing sequences when the number of Demazure operators we apply becomes large, and can we get some asymptotic information and so on. So this is this business. Yeah, so thanks for sticking to the end.
Thanks again, Thomas.
Sure.